Hi, everyone. It is my pleasure to introduce an excellent collaborator and friend, Dr. Rob Zellem. Rob is an exoplanet astronomer at NASA's Jet Propulsion Laboratory. He's working on ground and space-based observations of the atmospheres of exoplanets. Originally hailing from Philadelphia and then Hendersonville, Tennessee, Rob got his bachelor's degree in astronomy and astrophysics from Villanova University. He then went on to receive a master's degree in space science from the University College London and a PhD in planetary sciences from the University of Arizona. He's currently staff at NASA JPL and is a member of the Nancy Grace Roman Space Telescope's Coronagraph Instrument Project Science Team and the JPL commissioning lead of NESSI, a new multi-object spectrograph that will be used to study exoplanets. Dr. Zellem is also the project lead of Exoplanet Watch, which is a citizen science project that aids in the characterization of exoplanets. When he's not observing exoplanets, he enjoys jazz piano, cooking, and trying not to kill all of his plants. So without further ado, Dr. Rob Zellem.
Thank you. Thank you for that really nice introduction, Molly. Thank you everyone for having me and for coming out. I really appreciate it. Welcome to my TED Talk today. This is a giant monitor. This is pretty incredible. This is definitely the world record for me for giantest monitors or projections to ever give a talk to. So I feel like I'm gonna get lost in the center of this giant projector. This is really cool. It's a pleasure being here. I've been wanting to come up to ASU for years and just been blown away by the department, the people, the building's incredible. We have a Psyche model out there and some fancy 3D Earth and plate tectonics happening in the middle of the auditorium. So thank you again for having me and thanks for coming out to my talk. I really, really appreciate that. So as Molly said, I do lots of things to keep me sane, I guess, at JPL, from mission design work to doing my own research. I work on the Nancy Grace Roman Space Telescope, which is the next NASA flagship mission that's launching by 2027, named after Nancy Grace Roman, the first chief astronomer of NASA, sometimes called the mother of the Hubble Space Telescope. She's one of the true champions of space-based telescopes and observatories. But today, I'll be talking about one of my true passions, which is education, public outreach, citizen science, and small telescopes, which I did a lot in graduate school at some other unnamed Arizona school, maybe in Tucson, that we won't name because I know I'm in hostile territory. I'll ignore that. So here I'm talking about small ground-based telescopes are really crucial for space-based observatories. And here I'm trying to motivate why, with excellent things like Hubble, like James Webb, Spitzer, RIP, you still need ground-based, ground-based telescopes as well. Maybe it won't work. Well, let's see. Let me try to reset this really quickly. If not, I'll just hit the mouse. Or maybe my laptop died. There we go. Okay. So I know some of you might not be aware about transiting exoplanets. So I'll just give some quick backgrounds. If you know about this, just bear with me for a second. If we're observing a host star, if we're really lucky, there'll be a planet orbiting around that host star. And if we're even luckier, that planet will pass in front of the host star relative to our line of sight and block out the star's light and cause the star to appear to dim a little bit. And what's actually happening here is the planet is actually casting a shadow all the way back on us, hundreds of light years away. It's absolutely incredible. And this is called the transit method. This measures the dip in brightness of the host star as the planet passes in front of the star. And this really importantly tells us the size of the planet relative to its host star. The bigger the planet, the more light it blocks out, the dimmer the star gets. Conversely, the smaller the planet, the smaller the dip in light and brightness. And this method is used very, very importantly and successfully to also characterize the atmospheres of these planets. When a planet passes in front of its star, not only does the optically thick portion of the exoplanet's disk block out light from the star, but also the exoplanet's atmosphere absorbs some of that light. And if we look and analyze how the planet's atmosphere absorbs some of that star's light, we can actually infer the composition of the exoplanet's atmosphere as well. And this method has been used very, very successfully. It's been used to discover about 75%, about 3,000 of 5,000 currently known exoplanets to date. There we go. And the transit method has been used very, very successfully, both in ground and space-based telescopes. The Hubble Space Telescope there at the top right has used the transit method to characterize the atmospheres of about 50 transiting exoplanets. The James Webb Space Telescope, thank God it's working, yay, is now doing amazing observations of exoplanets at unprecedented precision and spectral coverage. It's just revolutionizing the field of every single new study that seems to come out every single month. We're finding molecules that were inaccessible to us from Hubble's wavelengths, and this is challenging and revolutionizing the field of exoplanets right now. This is really cool to be witnessing in real time. This telescope is truly ginormous, to use a technical term. It's about 6 to 8 meters across. That purple solar shield on the bottom is the size of a tennis court. If you aren't aware, it was so giant that it had to fold on itself like origami to fit in the nose cone bearing. I was lucky enough to see this at Northrop Grumman when I was out in Los Angeles and they were doing some testing. It was just massive, and it's incredible, such an incredible feat of engineering that they were able to get working. So it's really incredible. And James Webb is currently using the transiting method right now to study tens, if not potentially up to hundreds. Some estimate about 200 of exoplanets and characterizing their atmospheres. But looking beyond our current technology that's up there right now to the next generation of missions that are launching, there's one called Ariel. It's a European space agency that's here on the bottom right of this panel. And Ariel is a dedicated mission that will be exclusively detecting and characterizing exoplanet atmospheres. Ariel will look up at potentially up to 1,000 exoplanets. So what Ariel will do is it'll put the high precision wavelength measurements of James Webb into a larger statistically significant database. And Ariel will be launching at the end of this decade. And I would argue that the transit method is here to stay, that the next generation NASA missions as well will continue to use the transit method to detect and characterize exoplanet atmospheres. The HAPEX and LUVOIR missions that NASA recommended a hybrid version for the next NASA flagship mission, they do both have, at least I believe both of them have science cases to study the atmospheres of transiting planets around M-dwarf stars. But in order to observe a transiting exoplanet, we have to know very precisely when that transit will occur. Let's say I'm writing a proposal to get some time on Hubble or James Webb, and I want to study my favorite exoplanet. I write my proposal, dear NASA, I'm not a complete idiot. Please give me some time on this target. Pretty please, here's $1. Please observe my target at this date. I have to give them in my proposal an estimated transit of when I predict that next transit event will occur. So I'll look up on the NASA Exoplanet Archive. I'll look at archival data, someone that observed it prior to me, maybe a discovery paper, maybe a follow-up Hubble paper. And I'll say, hey, I think the transit will occur at this time. Unfortunately, though, some of those transit predictions, the timings, the periods of these planets, how quickly they orbit around their host star, a lot of these are now stale or imprecise. Some of them have uncertainties on the order of seconds, some of them minutes or hours. And on a one-by-one basis, sometimes this doesn't matter. You can sort of eat the extra time and just accept it for what it is. But if you start looking at the cost of any time on James Webb, or if you look at the 1,000 exoplanet sample that Ariel wants to get, even if all those planets have a 1 to 2 minute uncertainty, that's suddenly 1,000, 2,000, many thousands of minutes that are wasted waiting for your transit to occur by building an additional overhead. It's a waste of time. It's a waste of money. That's a waste of these very, very precious resources that everyone in the community, rightly so, wants to use for their own science. So you can build an extra overhead, you can wait longer and waste some time on these instruments, or you can do some pre-observing. You can go on the ground on your small ground-based telescope. You can get a transit of these targets. You can update their ephemerides, the next predicted mid-transit time, and we can use these telescopes a lot more efficiently and hopefully as a result maximize their science output. There we go. So I'm on the Ariel Case science team. CASE is a contribution to the aerial missions, NASA's contribution to aerial mission. Mike Line, who's a professor here, and General Strelnick as well, are both also working on CASE with us at JPL. And I was sort of freaking out, looking at this target catalog, realizing this issue with the timing, and the timing that could be wasted waiting for these transit events to occur. And roughly at the same time, we got some data from one of our collaborators that I have at Harvard-Smithsonian. They have a small 6-inch telescope that's completely robotic that's been observing for the last 10 years transiting exoplanets. It's out in Tucson, just downhill from the MMT. And we were looking at the data quality, and it's actually some sample data is shown here on the right. And we were quite honestly blown away about how this single 6-inch telescope, it doesn't have perfect tracking. All the PSFs look like little potatoes on the board. It lost tracking, and the target basically went across the focal plane by 200 to 300 pixels. The exposure times aren't optimized. There's no calibrations on this, no flats, no darks, no biases. And this thing is fully weatherproof. It observes in rain or shine. And the data quality is incredible. Just looking at what the single 6-inch telescope could do started getting us thinking. You know, this is a relatively dim star for a 6-inch telescope, about 11th to 12th magnitude, relatively small signal, about 1 to 3%. And we were honestly blown away that we can get science-grade data out of such a small robotic telescope. So then we started thinking of other ways, and we said, okay, we have this problem of needing these updated ephemeres. We have this opportunity to use this telescope. Let's do a little bit of a deeper dive. Let's now sort of extrapolate this precision here, this performance, to other needs in the field. So for example, come on, computer, there we go. What we did is we then forward estimated. We took the data from the micro observatory, looked at like 5 or 10 different observations, and we sort of estimated the capability of a single 6-inch telescope. We looked at all, I think, 4,000 exoplanets in the exoplanet archive at the time that are transitors. And what we did is we estimated how many of those transits could a single 6-inch scope hit and actually detect the transit with a 3 sigma detection significance. And we found that a single 6-inch scope can actually hit almost 200 exoplanets. So almost any given night in the year, there is a target that a single 6-inch telescope can observe with high degree of statistical significance. And some of these 200 targets have very uncertain mid-transit times that need to be followed up, that need to be refined to help out missions James Webb, like Hubble, like Ariel. So then we took it the next step further. We said, okay, given that these targets are available to a single 6-inch telescope, how much time could we actually save? And we did the calculations. We went on the NASA Exoplanet Archive. We looked at their mid-transit times that were published on there. Then we forward propagated those uncertainties into a few reference dates. We did one for James Webb right before it launched. We did one for Ariel, and we did one for an Astro 2020 mission that'll be launching in the 2030s. And we said, okay, what's the uncertainty of these mid-transit times if no one does any follow-up? And then what is the uncertainty if a single 6-inch telescope did this follow-up? And then what happens if you get a modest sized group, 16 6-inch telescopes, and did this follow-up? And we found that even a single 6-inch telescope could save tens of thousands of days of time. Just one 6-inch telescope can save us thousands of days of time that's wasted, that you'd be waiting for these events to occur. And if you expand that, just 16 people with a 6-inch telescope and give back to the community and help out and allow us to use these resources a lot more efficiently to enable perhaps more science. But ephemeris timing is fine. It's all well and good. There's other science cases that small telescopes can also achieve. So for example, you can do transit timing variations. When you have a planet orbiting around a star, it typically orbits, like every 3 days. If it's a hot Jupiter, you observe it transiting on a Sunday, and you'll see it the next Sunday, and the next Sunday, and the next Sunday. It's boring, great. But if you have an exterior planet in that orbit, the gravity of that exterior planet will tug on the inner planet. So one night, the transit might occur on Sunday. The next week, it might occur on a Monday. Next week, it might occur on a Saturday. And that's because the exterior planet is tugging on the inner planet and causing it basically to wobble and evolve in its orbit. And you can look for that shifting mid-transit time, and you can infer the existence of an exterior undiscovered exoplanet. So by using transit timing variations, which are needed over a long baseline, we can actually use this method to discover new, previously undiscovered exoplanets. And small telescopes are actually well suited for this. We can also use small telescopes as well to help us characterize stellar activity. In the field, this has mostly been done by a single or maybe one or two automatic telescopes. There's one out here in southern Arizona called the APT. There's the Assassin network as well. And we're getting photometry on a lot of these exoplanet host stars. The reason we care about stellar variability is because it can drastically change our interpretation of the exoplanet's atmosphere. So a planet that we think is clear might actually be cloudy, or a planet that's cloudy actually might be hazy. And that's been sort of borderline necessary to interpret Hubble data, but thanks to James Webb's superior sensitivity, it's even more crucial that we do this today. So what I'm showing here is some data taken with I believe the APT over a few years. And we're just tracking the stellar variability of an exoplanet host star. And these dashed lines and solid lines are showing some Spitzer observations we took. The reason we did this is because when Brian Kilpatrick did this study back in 2019, we thought we saw evidence for potential planetary variability. We see variability in brown dwarfs. It stands to reason that we would also see them on exoplanets as well. But we have to convince ourselves that the signal is not coming from the star. Remember, when you're doing transit observations, you're always looking for that signal relative to your host star. So what we did is we got some historic data that happened to overlap with the Spitzer campaign, and we were actually able to mathematically derive that the stellar variability of the host star was not inducing variability in the planet. So perhaps we're actually seeing variability changes in the planet's atmosphere itself. It's pretty incredible. You can also look for things called blended pairs. So if you remember that micro-observatory data I showed you with HAPD32, it's not perfect tracking, it's not perfect guiding. Every image is 1 minute long, regardless of what you're looking at. And as a result, you get these lovely potato shapes of the PSF, as the PSF as a star slews slowly over the exposure time on the focal plane of the camera. Well, you know, that doesn't look great. It looked like potatoes, like I said before, but it's actually very crucial to get this information. That's because TESS, the All Sky Survey that was launched by NASA a few years ago, has very, very large pixels in order to observe the entire sky, or at least large slices of the sky any given time of the year. So what can happen is two stars can sometimes look like they're one. You might be saying, why is this a big deal? And that's because, again, we're always analyzing our signal relative to the host star. And adding in the additional flux of an additional star dilutes the transit signal. So a transit depth that should be 1 to 3% gets down to maybe 0.5% or even 0.1%. And that starts getting into the the regime of you thinking that that planet is maybe a super Earth or a Neptune-sized planet. But in actuality, that signal is actually being diluted by a nearby companion star. And the planet you're actually looking at is a random, boring hot Jupiter. So you can actually do this and look into this a lot with these small telescopes. And this is exactly what the TESS SG1 group is. They're looking up TESS observations and discoveries, and then they're getting small telescopes to observe these fields and resolve stellar blends so we don't get confused and think that and misclassify planets as things that are smaller than we think they are. Excuse me. So looking into all these various science cases that small telescopes could do, I was also giving public talks because I love giving talks. It's a lot of fun. So like local astronomy clubs, I'd also have amateur astronomers come up to me afterwards saying, hey, this is somewhat interesting despite you being awkward and making really bad dad jokes. Can you tell me ways to get involved in this research? And I didn't have a really good reason or a good, good answer for them. But we had these science cases that had real needs. We had these issues on meeting these accurate times, and it just sort of clicked. There's thousands upon thousands of amateur astronomers across the world with really professional grade observatories. So perhaps we can leverage that and have them feed back to the professional exoplanet community. And then we launched a citizen science project called EXOPLANET Watch, which is inviting citizen scientists to observe and helping us monitor transiting exoplanets. So EXOPLANET Watch, as a citizen science project, we have both educational goals and scientific goals. Spent a lot of time talking about the science, so let's ignore that for now. But our educational goals are really to help educate and engage the public in exoplanet science to make it more tractable and connect them as well, and increase their confidence about their ability to do science. You get the public excited about your research, they're more excited to perhaps pay their taxes, and then that goes hopefully to us. Maybe, that'd be nice. But EXOPLANET Watch is a campaign to monitor routinely these transiting exoplanets, to update their mid-transit times, their orbital periods, to make them more precise, to enable us to use large observatories, both on the ground, like a Gemini or a Keck, as well as large space-based telescopes like Hubble and James Webb. We're a collaborative effort that we're aiming to be completely complementary to existing surveys. We have an open collaboration with EXOCLOCK, which is effectively the European version of us. They're trying to help out explicitly the European Space Agency aerial mission, where we're aiming more for helping out NASA efforts. We're helping out the Planet Hunters. We're a member of the TFOP SG1, which is that group that's doing ground-based follow-up and confirmation of test discovered planets, as well as single transiting exoplanets as well on long orbital periods. All of our data is immediately public to the entire community. There is no proprietary phase. Our pipeline runs every other night, and our website is immediately updated as soon as that pipeline is done running. This ensures that we're always up to date and giving you the latest values, but also so that data is immediately available to the entire community to update their timings, but also to do their own research if they wanted to as well. We also have community feedback for target requests. We've actually had 2 very successful campaigns. One in November, I think that was the world record for the longest transit event ever observed from the ground. It was an 18-hour transit. I think that was just accepted, you were telling me, Molly, just a few days ago out in the archive. We also had a big observing campaign back in December as well, I'll be talking a little bit about later, that required a large ground-based network to observe. One thing I'm also very, very proud of enforcing as well is that observers will be listed as co-authors on any published results. You do the work, you deserve the credit, and you should be co-authors on these papers. And we're sponsored by NASA's Universal Learning, which is funded by NASA's Science and Mission Directorate, SMD, and we're actually fully funded through the end of 2026, and perhaps also beyond that as well. So I just want to give a quick shout out to our EXOPLANET Watch team. We're actually a very small team. None of us work on this full time, so I don't know how we don't go crazy at all. We actually only have 5 JPLers that are staff on the project, and we're really awesomely blessed, honestly, to have some amazing interns. One might look a little familiar to some of you in the audience there, Izzy Huckabee, does amazing work for us at EXOPLANET Watch. So if you're interested in interning with us, we'll be opening a call for that probably in the next month or 2. You can go online and submit your application to the JPL internship opportunities and shoot me an email. I'd be happy to talk to you more as well. So I'll sort of walk you through the user experience. First, what you do is you plan your own observations. You can use whatever tool you want to observe any exoplanet you want. You want to observe HD 209458b, which has been discovered 25 years ago, and has been observed hundreds, if not thousands of times, go for it. We'll still take your data, because there's other interesting science cases we can be doing with such a long baseline of observations. We are partners now with the Swarthmore Transit Online Finder. This is what I personally use myself for planning my observations at Palomar, and they have our ranked list as well, published up on their website. So we make it easier for our users to figure out what planets are transiting and which ones we recommend that they observe given their location on the Earth. Then you do your own observations. Right now, we've launched out only to amateur astronomers last summer. And folks, that have access to a robotic telescope or their own data that they can make themselves. That being said, in about 2 to 3 weeks, we're going to be launching a data checkout system where we're going to have data spanning back the last 10 years from the micro observatory accessible for people to download and check out as well. I'll talk a little bit later about some scopes we also have in our network that we're getting up and running right now. So in other words, you don't need access to a telescope to fully participate in this project. You don't need clear skies. If it's randomly rainy and cloudy here in Phoenix, you can still get observations elsewhere in the world and analyze your data and contribute fully to this project. Then you analyze or reduce your own data. You don't upload it to some cloud server where they do the data analysis and reduction for you. You actually take part of this process yourself to learn the entire process about how multi-object photometry works and how people analyze transient exoplanet data. We have our own data analysis tool called Exotic. I'll talk a little bit more about that later, but you can use whatever tool you want. You have your own homegrown method that you like to use, go for it. You can reduce and analyze your data. The only thing that matters at the end of the day is in the right format and has the right information: time, flux uncertainty, and air mass. That's all you need to upload your data and contribute it to our project. Then you upload your data to the American Association of Variable Star Observers. This is the AAVSO. This has been I think the oldest variable star group in the entire world. They've been doing variable star measurements for the last 111 years. And at the time, when I was sort of launching Exoplanet Watch about 2 or 3 years ago, I was freaking out because we had everything figured out, except how are users going to upload their data to us at JPL? For some reason, I don't know why, but JPL doesn't like random people uploading data to JPL servers. Something about a security risk or some BS thing like that. So we came with this convoluted way of doing it through a Dropbox link. And I was reaching out to the AAVSO because they have amazing observers. And it's just a very natural partnership, and we can hopefully get the word out about our project. And just in passing, they're like, oh yeah, we also made an exoplanet database and you guys can use it. And I was like, thank God. And they're letting us use their database for free. And our users upload their observations to the AAVSO, and then we grab the observations from them. And it's a really great partnership. We're very lucky to be working with them. They helped get us many of our initial users, tens, if not 100 users. And let's see, about a year ago, we had about 2 years ago, we had about 100 observations. Now we have over a few thousand, which is pretty nuts. Then after you upload your data to the AVSO, you sit back, relax. If you're over 21, you crack open some beers maybe, and you can get published and you're included as a co-author. Or you can go on our website right now. All of our data products are there and easily downloadable. You can do your own study. If there's a favorite exoplanet of yours, grab our data, write a paper, publish us, scoop us. I hate writing papers, so please write them. That'd be great. The only thing we ask in return is you cite our paper and add an acknowledgement statement. And again, if you include any data from amateur astronomers and it hasn't been published before, you include them as co-authors. They do the work, they deserve the credit. So then what happens behind the scenes at JPL is we have our own pipeline that runs every other day. It's not a typo on Citizens, that's actually an acronym for something that I can never remember, so I'm not going to try to guess it right now. But what Citizens does is a fully automated pipeline with no human in the loop. What it does is it downloads the data from the AAVSO every other day. We then reprocess and refit the data with basically a tweaked version of Exotic. The reason we do this is in case any of the prior values, such as physical parameters like inclination, size of the planet, radius of the star, temperature of the star, if any of those values are updated, we can refit the data and make sure our data products are still valuable and relevant. Then, after we process the data, we immediately publish it to our website. Again, no proprietary phase. Try to keep everything open and make all of our data and data products. We show all of our fits, all of our posteriors, all of our measurements out there. So in case you don't believe a specific measurement, that's fine. You can still get access to the data and do your own analysis if you wanted to on it. And you can throw out data, you can add your own data as well. So I talked a little bit about EXOTIC earlier. This stands for Exoplanet Transit Interpretation Code. And this is something that Izzy has been a really great person that's been adding a lot of awesome coding and functionality to as well. EXOTIC is our own homegrown data analysis code. It takes your raw images taken from your telescope bits files. It does all the calibrations, the flats, the darks, the biases. It figures out your optimal aperture size, your sky radius, annulus size, figures out the best comparison star to use in your field. It also fits your data with a statistically significant light curve fit. And it gives you the output are things you can just drop right into a published paper. I can say this because we literally did this back in 2020. We used EXOTIC to analyze micro-observatory data and data from other amateur astronomers to make plots for our paper. So you're actually literally using the same tools that we use for our own research as well. This is all written in Python 3. You can download it locally on your own computer, but we also just launched 3 new versions of EXOTIC that run on the Google Colab Cloud. So you can run it as a Python notebook. You just need a free Google account. I think we all have at this point because we've all sold our souls to Google, right? So you just hop on Google. You can even run EXOTIC on your own cell phone. So you don't even need a computer to participate in this project at all. We have sampled data on our website. And again, we're working on adding the infrastructure within the next 2 weeks is when we'll do an alpha or beta launch, where you can also get data from one of our robotic telescopes. So you just need a cell phone to fully participate in this project, just a smartphone. Another cool thing that EXOTIC has is this real-time data reduction tool that we're showing here at the top right. This is actually built off some code that Kyle Pearson, our deputy science lead, built for our very long observing runs at the 61-inch on Mount Bigelow in Tucson, Arizona, because we'd be sitting there and transit observations are really boring. It's good when they're boring. You slew to your target and you sit on it for 6 hours. It gets boring fast, okay? And what we liked seeing was seeing a real-time quick reduction of the data just to make sure that we were observing what we were supposed to observe. And it also helped us stay awake a little bit. But we also realized the educational opportunity for this as well. When you're at a star party, when you're observing a transit, it's boring. You're looking at for a 1% dip. It's hard to see by eye. But you can run EXOTIC in real time, and you can point to your computer monitor while you're observing a transit and tell someone that, look, right here, we're observing an extrasolar planet hundreds of light years from us. It's blocking out its star's light, and that shadow is being cast back on the Earth. So hopefully I'll get some people interested in studying astronomy, or at least exoplanets. All right, so there's a variety of different ways you can get involved in our project. Currently, as I said, we launched last year to amateur astronomers because they already have a lot of the know-how and the instrumentation set up to immediately get involved in this project. And right now we're launching onto professional astronomers. That's why I'm here. Thank you for having me, Molly, to get the word out. And in January of next year, just in 2 months, we'll be launching out to the general public. And by doing so, we need to have data to give out to people who don't have access to their own telescopes. So right here is actually a picture of the micro observatory up in just outside of Tucson, downhill from the MMT. Again, they're fully weatherproofed telescopes, and they observe rain or shine. And they have on their hard drives data dating back from the last 10 years, hundreds of exoplanet observations that will now make accessible to our users so they can participate in this project. We're also working on right now of commissioning 2 new telescopes. One of them is our 0.4 meter telescope. It's in just outside of Wrightwood, California. It's part of the San Gabriels just outside of Los Angeles. And this was actually a picture taken from me from the observing run on the 0.4 meter. Giant Star Wars fan. We have 2 telescopes. So obviously this one's called Luke because it came first. Luke was born first. Giant nerd. Stay with it, guys. Come on. And what I'm doing now is we're trying to get this set up so it's fully automatic and robotic, as I enjoy sleeping sometimes. So hopefully every single night of the year, starting in a month or so, when we get our cloud sensor involved or installed, we can then use this telescope to make observations that we can also give out to our users. In addition, if a professional astronomer comes to us and says, hey, help us refine the ephemeris of this target, we can guarantee them that if it's observable in SoCal and it's not cloudy, we don't get rain, it's SoCal, we're in a giant drought. We can give them data on their object. We're also commissioning a 0.6 meter telescope that's been currently being refurbished right now. It's built in the 60s and things are breaking. But once this is online, this is the second telescope being added to our collaboration. So you can probably guess what it's being called. This is audience participation time. I have to make sure you're still awake, sorry. There we go. Oh, thank you, Star Wars nerds, appreciate that. So this one's being called Leia, giant Star Wars nerd. We also have access to a 1 meter telescope. We'll probably call it Jar Jar Binks or something like that too. But this will be online, hopefully in the first part of next year. So we'll have data from 2 observatories that we have complete control over. We have all that historic data from the Micro Observatory. We're still collaborating with them. They're still giving us data, so we'll continue to get data from at least 3 different telescopes that we can then give out to our users. So we also have ways of engaging our user base. This is actually been something that's been very important and really necessary to do. So we've had people come and get excited initially at the very beginning and then sort of drop off and forget about the project. So we have our website here that we've been doing a ton of work on to revamp, to make it a lot more user-friendly, because it was written by some weird scientists using lots of science terms that were not accessible to a general audience. We also have a monthly newsletter that we send out as well, and we give folks ideas about campaigns for observing. We also have these bi-weekly meetings that we advertise in our newsletter as well. And then very importantly, we have lots of memes as well on our Slack channel. So here's Kaya doing our Monday morning meme as well. That's a good one. We have like Wildlife Wednesdays on Wednesdays. I always post a picture of Rebecca Black on Fridays because it's Friday. If you don't know who Rebecca Black is, I apologize for the Googling you'll be doing later this afternoon for getting that stuck in your head. And it's been great. Our users can directly interact and are probably slacking me right now, but also we're trying to foster that sense of community where our users can help each other out as well. Because my entire goal in this is to not only make this project open for everyone and anyone and as inclusive as possible, but also so we have no human in the loop. God forbid I go on a vacation. I don't want the project to die or go on pause so I can have my Mai Tai, right? I want the project to still keep on going. So our pipeline is completely automated and automatic. And all of our analysis is automatic and automated as well. We use tons of statistics. And by tons, I mean we do a 3 simile clips. It's not a big deal, to assess the quality of the data. And here's some really cool results that we actually just published about 2 or 3 weeks ago that Kyle Pearson, so his name got cut off here on the right, published. But we have, actually these numbers are already out of date. We've had about 10 more users sign up over the last week. So we have over 709 users over 22 time zones. That's pretty mind-boggling. So we cover about 75% of the sky. That's nuts. These numbers are also out of date. We just hit our big milestone of 250 targets, even though we have a limited launch. We really started working on this about 2 to 3 years ago. For context, I was hoping to get maybe 200 targets in a year or 2 from now. Now we have 250. I never thought this would happen. I was hoping to maybe get 500, 750 observations a year from now. We're actually already over 1,200 observations as well. We have some users that are all over the world, in Japan, in India, in Europe, North America, Australia, New Zealand. We have a guy just outside of Los Angeles who's observing every single night with this small telescope. We don't need dark skies. We have people using 4-inch telescopes, 10 centimeters across, that are uploading really precise, high precision measurements and observations to our collaboration. We don't need big telescopes. We can still do impactful science, and our users are excited to help out with our project. So if any of you would like us to help observe with the stellar variability, through ephemeris maintenance, look and resolve stellar blends. We like to give a talk to our users. They love hearing from all of you. They would love to help out. They get really excited and get really gung-ho whenever we have these big observing campaigns. So if you're interested, please definitely do reach out to me. And then we saved about a third of an hour. This actually used to be a much larger number, about 3 hours this summer. But since then, ephemerides have been updated due to efforts by other groups, by people that have published test data, by the EXOCLOCK network. So, but again, depending on how you count, about an hour of time on James Webb costs about $1 million, if I've done my math correctly. So if NASA wants to cut me a check for $317,000, that would be awesome, because LA is expensive. And then back in December, we actually had this really big observing campaign in support of some James Webb observations. We took data of this exoplanet called HD 80606b. It's one of the most eccentric exoplanets because it has a very oblong orbit, and its atmosphere changes its temperature by hundreds of degrees as it gets closer and farther away from its host star. And there are some observing campaigns of James Webb that want to observe this atmosphere of this exoplanet and see if it changes or evolves as it's heated differentially over its orbit. But HD 80606b had an imprecise ephemeris, and also it has a 12-hour-long transit duration. It's impossible for any single user across the globe to observe this target. So what we did is that some of the people on that proposal came and requested we help observe this target, and we got our network activated across the entire world. So we actually had people in Eastern Asia, in Japan, and India who first started observing the transit in December. They passed it off to folks in Europe, then back to folks in North America, and then some people who observed the transit on one night got the end of it on the second night. This was absolutely crucial as well because, of course, the entire northern hemisphere basically was clouded out. I remember looking at the cloud maps and just seeing clouds almost everywhere in the northern hemisphere and freaking out. But luckily, there was patches of sky here, here, and here, and we're saved. We had about 26 observatories, 24 facilities involved, all with small telescopes under 0.7 meters or about 30 inches. And we probably had another factor of 2 or 3 more that wanted to participate in this project that were clouded out. It really shows why you need a large dispersed network so you can overcome things like weather and clouds. And if you look at the data on the right, again, this is written by Kyle Pearson, our deputy science lead, who published this paper just a few weeks ago. If you look, on a one-by-one basis, some of this data quality does look a little dubious, right? Looks like it has high scatter. You'd be hard pressed to say, oh, that's a great transit detection. I will totally admit that. Some of this data, as you look on the left, are coming from 4.5-inch telescopes from Unistellar's EV scope. But when you take all this data and you combine it together, you get a really nice looking light curve. And you can see it actually looks very high precision. When we take all that data from those multiple small telescopes across the world, we get a very nice detection of the transit. And this actually improves upon the observations by tests that were taken a few years prior to it as well. And by using all this data together, we were actually able to save a bunch of time on the next predicted transit, as well as the next predicted eclipse time. I think we saved over an hour of time on these observations. So James Webb owes me $100, lots of money. That'd be great. $90 million. That'd be nice. Molly, I don't think you think I'm going to get the cash. No. So we also have tons of published papers already, which is just mind-blowing to me. These are actually required by NASA. In order to call us a citizens in science project, we have to have citizen scientists on peer-reviewed papers as co-authors. And if you look at this list, there's Kyle's paper right there. There's this weird dude, Zellem et al. From 2019 and 2020. The rest of these are our citizen scientists. They're leading their own peer-reviewed studies as well. They're publishing their own results. And about 3/4 of these are high school students leading their own science results. Yeah, it's absolutely incredible. So we totally encourage people to go to our database, to request data, to publish your own surveys. It helps us out a lot but hopefully it also helps those folks maybe get into undergrad or grad school and lead their own collaborations. We also have folks all across the world that are including students as well. So whoever that weird person is at the top, I think they're including Exoplanet Watch in their class on WASP 104B. They're making some really cool, impactful science I can't talk about too much, but I think you see something super cool in it. So keep your eyes peeled for a paper in the next 30 years, maybe, probably. Cool. We have people all across, not only the US, San Diego with Brief. We have people in Australia, Brisbane, Harper College, I believe is somewhere in the Midwest. We have a high school instructor, Colette Talk, who includes Exoplanet Watch as part of her curriculum. A lot of these people either use their own telescopes or more often than not, archival data from the micro observatory. And they include that in their lab instruction. And then some of these people even take the next step, most of them do, and publish their own peer-reviewed papers as well. All right, so I think I'm at the end of my soapbox presentation here. Thank you so much for your time. If you're interested in getting involved or participating or collaborating with us, or if you have any feedback, we live and die by the feedback of our users. Our project has grown significantly in such a positive way, thanks to people suggesting new features we add to our code. Please reach out. You can email us at exoplanetwatch@jpl.nasa.gov. You can try to memorize that URL. I'm horrible at that. So just Google NASA Exoplanet Watch, and we should be the very first link that pops up. And with that, I'll take a sip of water and a breath. I'm happy to take any questions. Thank you.
Any questions from the audience? You're gonna just wait for a microphone and it'll come down to you so we can hear it online. There you go.
Hi, Rob. Great talk. Thank you so much. I just had a quick question about the software that you talked about. The analysis pipeline, does it have instrument, as in telescope-specific calibration processes, or is it more generally built, and then you kind of work one-on-one with each group that take observations?
Yeah, so we actually find that most of the systematic errors are actually luckily treated by the use of comparison star. And that gets rid of most of the shared systematic errors in the data set that seem to dominate the error in the time series. The next big one after that is error mass variations. That's on the order of 10 to 30%, some bad cases. So we do that division by comp star, remove the shared systematics, and we put the residuals after that with an error mass correction curve. And that's all we do. And we're getting thousands of really nice looking data sets. You do have to enter your telescope information. That's more for really record keeping, honestly. And that's about it. It doesn't do anything very, very special. But if you have a scope that you love using and you have some sort of unique sort of part of the data that we have to treat, let us know. We're always more than happy to build that functionality into Exotic as well. Thanks, great question.
Thank you.
Nina, there's one in the middle of the room, and while we're waiting for that microphone, I've got a couple online here. So one asks, sorry if you've already gone over this, I might have missed it, but how often is the pipeline updated? And then what other characteristics does Exotic give you besides the transit dip?
Yeah, so Citizens runs every other night, at least it should be. And if it isn't, let me know because there's a problem there. So our website is updated every other day as well. We are putting this off for a little bit for right now, but the goal is after we get to the craziness of our general audience launch at the beginning of 2023, is we'll run the pipeline every single night. Right now, we're being a little silly. We're reanalyzing, re-downloading everything at once. What we want to do is finally flip on the switch that enables a feature that only updates things that need to be updated, i.e. only download new data, only reprocess new data, or reprocess old data if your priors have changed from the NASA Exoplanet archive. And then the other question about Exotic was?
Just what other characteristics does Exotic give you besides the transit dip?
Tons of information. Right now, what it does is it gives you the full statistically significant information on the light curve fits. It uses a nested sampler to fit our Mandel and Eagle light curve models to our transiting exoplanet data. It gives you the transit radius, all of those values like RP per star, A over R star inclination, the limb darkening coefficients, as well as their reasonably derived uncertainties. So you can report them directly in a published paper. Last week, we also added a feature to Exotic that if you have a comparison star in your field of view that is a flux standard, you can also grab the stellar variability information out of your host star. You're getting the host star for free in these transit observations, so you might as well also get the variability information about these host stars as well. There's also lots of helpful diagnostic plots, air mass versus flux versus centroid position that we all give an Exotic. But if there's something missing, something you would like to see, let us know and we'd be happy to add it as well. Thanks.
Hey, thanks for a really great talk. My question, so you mentioned that a lot of the publishings were from high school students. So does your team provide resources for the citizen scientists to like carry out and publish their own surveys, or are these just really advanced 16-year-olds?
Yeah, so a lot of these were done by Kalei Tuck at Stanford Online High School. And hopefully we'll be getting also a publication or a few from Molly's class as well. And a lot of these are done mostly right now by us giving them a few years or a few observations of one specific planet. They'll study that exoplanet in depth and update the ephemeris of that exoplanet. We would love people though to go to our results page right now and take what you want from it. If you have a TTV observation you want, go ahead and publish that online. I kind of hope you do and kind of hope you don't scoop us. I hate writing papers, but I need to write papers because JPL likes it for whatever reason. But you're more than welcome to go up on our website again and grab any of our data products. So if you see something interesting in there, go ahead. It's all on our website right now. And there's no paywall, there's nothing you need to click to download. The only thing that's on there is a little link that you can click easily, and it'll actually write most of an email to the AAVSO. So you can say, hey, here's this observer code. We use observer codes to US privacy laws. Can you hook me up with this observer's identity so I can invite them to be a co-author on our paper? And then just cite our paper, write as an acknowledgement. So that answer your question?
Yeah, thanks.
Cool.
I have another online here, and we'll pass the microphone there. Let me see, have you looked at the effect of using Exoplanet Watch on students' self-efficacy within a classroom environment?
I personally have not, but I know folks like Molly, who's currently doing that right now with Heather, and also Kalei has been doing that a lot, as well as other educators such as Pat Boyce. So that's basically the short answer there. I'm a scientist is my background. I'm making this up all as I go. That's why I'm so excited to work with people like Molly, because they can tell me what I should be doing differently and better.
Hi, thank you for the talk. I was just going to ask, I know that with a data set this large, you end up with inevitably some small amount of unusable data. Where within that collection to processing to publishing pipeline do you cut off that data, and what is the good data versus bad data cutoff that you decide?
That's a great question. So what we do, because again, I like to sleep, is we have it fully automated in our pipeline. So typically, if you go to our results page, we probably should have put a screenshot up here. We show all the light curves from all the data that's been contributed to our project. We don't try to sweep anything under the rug. And you're going to see some light curves on there. The data does not look great. Some users might have accidentally looked at the wrong target star. Someone maybe looked through a cloud, or they opened their dome the wrong way and had the pointing wrong, whatever. That's why we refit the data. So we refit the time series with Exotic, and we look for 3 sigma significant detections of the transit depth. If it's below that, we don't allow it to leak into our O-C plot to calculate the new transit ephemeris in the orbital period. That being said, though, if you look back at those 806.060 observations, each of those individually are not significant detections of the transit. So the next thing we're going to be thinking about doing is experiment and see if, maybe a single data set might be a 1 sigma detection or a 2 sigma detection. If you bin it all together, you can get something statistically significant. That's just work that's outstanding that we have to do.
Thank you.
Excellent. Anyone else in the auditorium here?
Hi, I was just wondering if you have any initiatives to encourage students and us citizen scientists who are from groups that are typically underrepresented in STEM to participate in Exoplanet Watch.
That is an excellent question.
Let me add, there's a question just
Sure.
like it online that I've
Perfect.
just worded a little bit. Do you know the demographics of your citizen scientist? And do you anticipate that more diversity of contributors after the telescope loaning program?
Yeah, that's all excellent questions, and something that's very near and dear to my heart. Right now, by launching out to those amateur astronomers, it's typically old white dudes that are retired and have tons of money to buy nice telescopes. That's basically our audience, mostly for now. But thanks to people like Calais for getting high school students involved, other folks across the world, we're getting more student involvement, people that are younger, that are more diverse as well, based upon their background. And I'm hoping that this eventually will lead to more people being involved in a later part of their life in astronomy. And like the other question online said, I'm very hopeful that the data that we're able to give out to people eliminates that financial barrier to have to purchase a telescope at all to participate fully in this project. We are also starting a telescope loan program. We have six 6-inch celestrons on equatorial mounts with digital cameras that we're looking to loan out. First, probably in the Southern California, Los Angeles area, to have to drive out there and fix something, but we're looking to give them out to community colleges, museums, libraries, historically Black colleges and universities, minority serving institutions as well. And that is something we are definitely going to be pushing hard on this next calendar year when we launch out. Rachel Zimmerman Brockman, who's our outreach chair, she has a very long list of all of these institutions, not only the big names like an ASU or University of Arizona or other maybe WS universities as well, but also the smaller ones that might not have the funding to purchase their own telescope or might look at their 4-inch telescope and think, this is a piece of crap, no one wants to use it. You can. These are actually very big, these are very hard issues we're actually fighting against. There is unfortunately this elitism, both in the professional and also the amateur community, that you need dark skies, you need giant telescopes that are stupidly expensive. That's not the case. We had a student from Caltech who used one of our 6-inch telescopes from the top of the astronomy building in downtown Pasadena and contributed his observations to that 80606 campaign. That cost about $1,500 to buy off the shelf. That's still expensive though. I don't want to spend $1,500 on a telescope. That's why we're getting that data from our telescopes to then give out, so that all you need at the end of the day is a smartphone. Most people do have. That being said, any of you have any ideas on how we could do a better job to engage more audiences, to increase our DEIA issues, please let me know. This is something that's very near and dear to our entire team's heart. We're always looking for suggestions as well. So thank you again for asking that. Appreciate it.
Thank you.
So cookie time, right? Cool. Well, thank you again, everyone, for having me. Really appreciate it. It's been a pleasure coming here. And hopefully you sign up and participate.